Dear students, welcome. You are about to listen the a deep dive into a single most important concept in the computational fluid dynamics, which is the discretization. So before we start, take a deep breath. I promise you by the end of this session, you will never look at a curve, a pipe, or a weather forecast the same way again. You will see the hidden skeleton of the points and the lines that make modern simulation possible. So let me ask you a question. How many points are there on a surface of your microphone? If you say infinite, you are correct mathematically. But how many points does your computer's memory have? Maybe finite, maybe 16 billion bytes. So that is a huge number, but still finite. So how do we force an infinite continuum into a finite machine? This is an art of discretization. So let us begin. By the end of this session, you will be able to explain why partial differential equations cannot be solved directly on a computer, derive a finite difference approximation from a Taylor series, and understand the error you just introduced, and distinguish between the finite difference, finite volume, and finite element methods, and how and know which one is used in fluent open form and why. Define the truncation error, the round of error, and the CFL condition, and tell me what happens when you violate it. And at the end, you would spot a bad mesh from a mile away and avoid the most common discretization disasters. So, uh, imagine you are standing on a beach and looking at the ocean. The water surface is smooth, continuous. Every point has a height. Every wave flows without jumps. So this is the continuum assumption of the fluid mechanics. The equations that describe this are the Navier-Stokes equations, and these are essentially the um, uh, partial differential equations, PDEs. So they involve rates of change, how velocity change in space, how pressure changes in time. They are beautiful, exact, and except for a few simple cases, impossible to solve analytically. Why? Because a PDE describes an infinite number of points. To solve it exactly, you would need an infinite number of equations. So your computer, no matter how powerful, cannot do the infinite calculations. So we cheat. We say, I don't need to exactly know the velocity at every single point. I only need it at a finite set of selected points called nodes, or the grid points in between, I guess, interpolate. So that act of replacing a continuous domain into with a finite set of discrete points is spatial discretization. So let me give you an analogy I use with my students most often. Take a fresh loaf of bread, the whole unsliced loaf. That is your continuous solution, smooth, unbroken, and complete. The recipe for the dough is the Navier-Stokes equation. Now, discretization is an act of slicing that particular loaf. The knife is your grid or mesh. Each slice is a control volume or element. If you cut very thin slices, say 1 millimeter each, and you get many slices, when you reassemble them, the stack looks exactly, almost exactly like the original loaf, but it takes a long time to slice, and your plate, the which is the computer memory, fills up quickly. So if you cut the thick slices 5 centimeter each, for example, you finish fast. But the reassembled loaf has a jagged stair step shape, so you lost the smooth crust. In CFD, thin slices mean the fine mesh, high accuracy, long computation time. On the other hand, the thick slices mean the coarser mesh, low accuracy, and the faster computation. So your job is to choose the slice thickness that is just enough to capture the physics you care about. So the space is not the only thing we slice. We also slice the time. Suppose you want to simulate how a ball drops from a table to a floor. That continuous motion is a smooth parabola, but your computer cannot compute at every infinitely simul instant. You choose time steps, for example delta t equals 2.01 seconds. At t equals to 0, you know the position and the velocity. You use the physics to predict position at this time, t equals 2.01. Then you update, predict again, and so on. This is time marching problem. The size of delta t is very crucial. If you take delta t very large, the ball might jump through the floor without registering the impact. A classic discretization error called temporal aliasing. If delta t is very small, on the other hand, you simulate for so many days. So discretization is always a trade-off. We accept an approximate answer because the exact answer is unattainable. The skill of a CFD engineer is to make the approximation good enough for the engineering decisions. So here is the paradox. The more you discretize, which means the finer mesh, the smaller time step, the closer you get to the continuous truth. But also, the more operations you perform, the more round of error accumulates. We will cover that later. But and there is a second paradox too, that discretization also creates the numerical diffusion, an artificial smoothing that washes out the sharp gradients. Yet without discretization you cannot solve at all. So we live with this particular tension. As the famous statistician George Box said, all models are wrong, but some are useful. Discretization makes CFD very useful. So let us now look under the hood. How do we mathematically convert a derivative into a simple subtraction? So open your mind into to one equation. This is the most important equation in all of the numerical analysis, which is the Taylor series. So let phi be the function, say temperature along the road. We know that its value at a point x. uh, what is its value? A small distance delta x to the right at x plus delta of x. So we can equally we can see this by this particular expansion using the Taylor series. So the future equals the present plus the slope times the step plus a bit of curvature plus a tiny bit of jerk, and so on. So if delta x is very small, the higher order terms delta x squared, delta x cube, and so on becomes extremely tiny. So we can truncate the series after the first derivative term. But and this is crucial, we are not interested in phi x plus delta of x directly, but we want the derivative partial phi over partial of x, so we rearrange it. So look at that. The first term on the right uses only the two known values of phi and the step size delta of x. That is the finite difference approximation of the derivative. This stuff in the curly braces is representing the terms we ignored, that is the truncation error. We have successfully turned calculus into algebra, but we paid a price. We introduced an error proportional to delta of x, which is the first order or the second order delta x square, depending on how many terms we wish to keep. So let me explain the order of accuracy, because you will see this everywhere. Second order upwind, first order Euler, etc. Such type of terms. So if we see the leading term in the truncation error, if that leading term in the truncation error is proportional to delta x and raised to the power 1, we say that the scheme is first order accurate. Half delta of x, error halves. So if the leading term is proportional to delta x square, the scheme is second order accurate. Half delta of x, error reduces by a factor of 4. Now why does this matters? Because a second order scheme gets much more accuracy for the same mesh refinement. In practical CFD approaches, first order is too diffusive. It smears the shocks and the boundary layers. Second order is the minimum for production work. Third order, however, and above are used in research or very sensitive flows like aeroacoustics. So, from the same Taylor series, we can build the different approximations. The first difference is use the point I and I plus 1 as displayed. The backward difference, which uses the I minus 1 and I, the 2 points, and the central difference, we can write the Taylor series about the 2 points I minus 1 and I plus 1 as displayed over here. So that is the second order accurate. Why? Because the central difference has the term of have the terms remainder terms of the order of square delta x square, and delta x square terms cancel out. Now, the second derivative used in the viscosity terms add the two Taylor expansions instead of subtracting, as displayed over here. This particular equation, these are the building blocks. Every CFD solver, no matter how complex, ultimately replaces every derivative with combinations like these. But here is the catch: these formulas assume a uniform grid with constant delta of x. Real grids are rarely uniform, then the formulas become more complicated, but the principle is the same. So we move on to the grid methods like FDM, FEM, and FEM. Now that we have finite differences, let us talk about the methods that use them. Finite difference method, FDM, is the oldest and conceptually simplest. You overlay a structured grid, usually rectangles or cubes, onto your domain. At each grid point, you replace each PDE derivative with a finite difference approximation. The result is the system of algebraic equations that you solve. Now, pros to this is very easy to derive high order schemes such as the fourth order or the sixth order, computationally efficient on the simple geometries. Now, there are disadvantages to that also. The grid must be structured like a checkerboard. Curved boundaries are approximated by the stair steps or require complex coordinate transformations. FDM, which is a finite difference method, also does not naturally conserve mass, momentum, and energy unless you are very careful. Whereas FDM used in academic codes for turbulence research in weather models like the Earth's atmosphere can be mapped to a sphere like with latitude, longitude grids, and in some commercial codes for simple duct flows. But for industrial CFD with complex shapes, a car engine, a human artery, FDM is very rare to use. Now moving on to the finite volume method, FVM, which is often considered as the engineer's workhorse. So every finite element method, this is the king of the commercial CFD, including the codes like Fluent, CFX, OpenFOAM, Star CCM Plus, all uses of FVM method. Instead of points, FVM divides the domain into control volumes or cells. The governing equations are integrated over each cell. Then the divergence theorem, which is the Gauss's law, converts the volume integrals of divergence into surface integrals of flux. So what flows into a cell minus what flows out must equal the accumulation inside. This is exactly the physical principle of conservation. Therefore, the FVM is conservative by construction. Even on a coarse, dis- distorted mesh, mass and momentum balance exactly. FVM also works on unstructured meshes, triangles, tetrahedra, hexahedra, prisms, so you can fit them to any geometry, a turbine blade, a human face, a Formula One car. So the price, the math is heavier over here. You need to reconstruct the gradients at cell faces, and you have to be very careful with the non-orthogonal cells. But the robustness of conservation makes FVM the industry standard. So if you will ever use FDM in your job, chances are you will use the FVM. Now moving on to the finite element method, the which is the structural analysis tool also, and finally FEM. This method is originated in structural mechanics. You divide the domain into elements using triangles and quadrilaterals in 2D, tetrahedra or bricks in 3D. Inside each element, you assume the solution is a simple polynomial, either linear, quadratic, etc. Then you glue the elements together by requiring that the solution is continuous across boundaries. So this gives you a global system of equations. FEM is extremely powerful for problems with complex material properties or anisotropic diffusion while in CFD, FEM appears in CFD for fluid structure interaction type of problems, for example, a wing deforming under aerodynamic loads, and in higher order spectral element methods for turbulence research. However, for standard FEM for fluid flow can suffer from numerical oscillations unless special stabilization terms are added, like SUPG, which is often abbreviated uh, as streamline, upwind, Petrov Glerkin method. So the summary of all this discussion is that FDM uses a simple math, the structured grid, not conservative in essence, while FVM, which is a finite volume method, is conservative. Unstructured can also work, and it is the industry standard. FEM, finite volume method, is flexible, great for the solids, needs stabilization for the fluids when it is used in the fluid structure type of the problem, fluid structure interaction type of the problems. So for the rest of this lecture, we will be focusing more on the FVM approach, finite volume method, because it is the most relevant to the real world CFD, but the discretization concepts apply to all of these. Now, we move on to the errors why the accuracy goes to die, in which the first one is a truncation error, the price of chopping the Taylor series. We have already met the truncation error earlier in the earlier slides. It comes from ignoring the higher order terms in the Taylor series, but let me make it very visceral. Take a simple function phi of x equals to sine of x. The exact derivative at x equals to 0 is cos of 0 equals to 1. By using the finite difference with x, delta of x equals to zero point 0.1, the error is approximately 0.0017. But when we use the delta of x equals to 0.01, the error would be very much small. It would be point four zeros and 17. So half delta of x 10 times, the error would reduce by a factor of 10. This is the first order. Now, truncation error manifests in CFD as numerical diffusion. Imagine simulating a sharp interface between the hot and the cold fluid with first order schemes. That sharp interface becomes a smeared gradual transition, like stirring cream into coffee. With second order schemes, this interface stays even sharper. So that is why you never use first order to for final results. It is too blurry. Then there comes a round of error, which is related to the computer's finite memory. Truncation error decreases as delta of x decreases. So why not make delta of x infinitely small because of the round of error? Your computer stores numbers in finite precision, typically 64-bit double precision, which gives about 15 to 16 decimal digits of accuracy. Every time you add, subtract, multiply, or divide, you lose a tiny bit of precision. Now imagine a mesh with 10 million cells. You perform 1,000 iterations. This is 10 billion operations. Now, the tiny error accumulates. Eventually, you can swamp the solution. Worse, when you subtract two nearly equal numbers, for example, phi I plus 1 minus phi at the node I, where phi varies very slowly, you get catastrophic cancellation. Most of the significant digits vanishes over here. So there is a sweet spot, delta of x small enough to keep truncation error low, but not so small that round of error dominates. In practice, for double precision, you rarely go below 1 exponent minus 12 relative step size. For most engineering meshes, round off is negligible compared to the truncation error, but it exists. Then there comes the great independence study, finding the sweet spot. How do you find the optimal mesh? You perform a great independence study. You run the same simulation on three meshes, coarse, medium, fine. Plot a key output, say drag coefficient versus the mesh size or the number of the cells. As the mesh refines, the solution should approach a constant value, the great independent solution. When the change from medium to fine is below your tolerance, for example 1%, you stop. Never trust a CFD result that has been checked for grid independence. It is the single most common reasons for the wrong answers. So never trust a CFD result that has not been checked for the grid independence. So two more errors for completeness are the iteration error and the modeling error. So we will be discussing them one by one. Iteration error, most CFD solvers solve the algebraic systems iteratively. They guess correct, guess again. So you stop when the residuals drop, say by 1 exponent minus 6, that residual is not zero. You have iteration error. The other type of the error is the modeling error. Discretization only approximates the equation you gave it. If you use the wrong turbulence model or the wrong boundary condition, even an exact solution of the discretized equations will be wrong. So remember the hierarchy, that modeling error greater than the discretization error is greater than the iteration error is greater than the round of error. So always fix the largest source first. Now moving on to the next part, which is about the stability and the CFL condition. Have you ever run a CFD simulation and suddenly the temperature becomes NaN, not a number, which is an abbreviation of NaN, or the velocity goes to infinity? Uh, the simulation exploded, or which is often termed as the numerical instability. Instability does not mean your physics is wrong. It means your discretization scheme is unstable for the chosen time step and the mesh size. Think of a child on a swing. If you push at exactly the right moment, the swing goes higher, which is a stable. So if you push randomly, it might stop. If you push too hard, it flips over, which is unstable. In CFD, instability usually grows exponentially until the number overflows. The most famous stability condition is the Courant Levy Fredericks condition, CFL condition. So let U be the flow velocity, delta T the time step, and delta X is the mesh spacing. Define the CFL number as C equals to U times delta T divided by delta of X. So what does it mean physically? That it in one time step, a fluid particle travels a distance U times delta T. The mesh cell size is delta of x. So if c is very less than 1, the particle travels less than one cell width. The solver can see it move across the cell, which means stable. If c equals to 1, the particle travels exactly one cell, which is a borderline. If c is greater than 1, the particle jumps over one or more cells without the solver registering its passage. So the solver tries to update based on incomplete information, and the oscillations explode. For explicit time of for explicit time schemes like the simple forward dialer, the necessary and Sufficient condition for stability is that CFL must be less than equal to 1. In practice, we keep CFL condition less than equal to zero point 0.8 for safety. For implicit type of schemes, the CFL condition is not a hard limit. You can use C equals to 10, 100, or even 1000 and still be stable. But accuracy degrades if C is too large. So let me clarify explicit versus implicit integration because it is crucial for choosing the delta t. For explicit time stepping, the future state time n plus 1 depends only on the current state, that is a time n. It is easier to code low memory per iteration. Stability condition is CFL less than equal to 1. Very small delta t for the finer meshes or higher velocities, and it is slow to reach the steady state. While on the other hand, implicit time steppings, the future state depends on both the current and the future states. You must solve a large step system of equations matrix at each time step. It is harder to code. Higher memory would be needed. Unconditionally stable for the linear problems. You can take huge delta t. Each time step is expensive, but you need far fewer steps. Now, talking of the analogy, explicit is like the climbing is like climbing the stairs. You always know where your foot is. Implicit is like jumping across the chasm. You must plan the landing. But you get there faster. Most industrial CFD solvers use implicit methods for steady flows and explicit only for the very fast transients. For example, shock waves, where accuracy demands small delta t anyway. The CFL condition is for advection flow moving, but diffusion viscosity imposes its own constraints. Here we can see a particular equation which is particularly for the explicit scheme, that d must be less than one half, where nu over here is the kinematic viscosity. This is much more restrictive. Halving delta of x means you must divide delta t by 4 to keep d less than equal to zero point 0.5. Source terms like chemical reactions can also cause instability if delta T is too large relative to the reaction rate. So in practice, your solver will automatically limit delta T based on these criteria. If you ask for adaptive time stepping, but if you set a fixed delta t, you must ensure it satisfies all the constraints. We have talked about the discretization schemes, but they are meaningless without a mesh. The mesh is the skeleton on which discretization lives. So, first of all, the structured meshes, all cells are hexahedra bricks arranged in a regular IJK pattern. So pros are that it is fast to compute, low memory, easy to implement higher order schemes, and the cons are that it is difficult to fit to complex geometries, requires the multi-block decomposition. On the other hand, unstructured meshes, the cells can be tetrahedra, pyramid, prisms, or arbitrary polyhedra. Advantages can it can fill any shape automatically, easy local refinement, and only disadvantage is that it may consume higher memory, slower to compute, and more complex data structures. So most commercial CFD solvers uses hybrid meshes, a prism layer near the walls to compute the boundary layers, and tetrahedra or hexahedra in the core region. A bad mesh will ruin even the best discretization. Here are the three metrics you must check. First is the aspect ratio. Ratio of the longest edge to the shortest edge in a cell. Ideal value is 1, which is representing the cube. Acceptable is that it must be less than 10 for most flows, less than equal to 100 for the in the boundary layers where flow varies only in one direction. And when it is dangerous, then and when the aspect ratio is greater than 1000, the solver may diverge. The second key matrix is the skewness, how far the cell deviates from an ideal shape, equilateral triangle, or the square. So when the skewness value is 0, it is considered perfect. If it is 1, it is completely flat. Acceptable is when its value is less than 0.85, and dangerous is when its value is greater than 0.95, which means it would have high truncation error. And the third and the most important is the uh, orthogonality metric, which represents the angle between the line connecting the cell centers and the face normal. Uh, Ideally, 0 degree is the perfect alignment for the orthogonality condition. Acceptable is when its value is less than 20 for most of the solvers, and dangerous is when its value is greater than 70 degree, and which means that the flux calculation becomes inaccurate. So most CFD preprocessors like ANSYS meshing, pointwise, and gambit meshing have tools to visualize these metrics, so never skip the mesh quality check. Finally, a word about near wall meshing is that the turbulent flows have a very thin region near the wall where the velocity changes rapidly, which is the boundary layer. So if you do not resolve it, your drag and the heat transfer will be wrong. So the dimensionless wall distance here is the y plus, and it is represented by this particular equation where y is the height of the first cell of the wall. If y plus value is approximately equal to 1, you are resolving the viscous sublayer. Uses it may use a low Reynolds turbulence model and a very fine mesh, and it would be representing a very fine mesh. But if y plus is in the range of 30 and 300, you are in the uh, log law region. Use wall functions over here, and it would be representing a relatively coarser mesh. So your choice depends on the problem. For aerospace, y plus is approximately equal to 1 in common. For industrial heat exchangers, y plus is often in the range of 30 to 100, and it is often acceptable. Always compute the y plus after your simulation. If it is too high, your wall treatment is invalid. But if it is too low, you wasted the computational resources. So let us solidify everything with a concrete example. Suppose we have a problem over here that a straight pipe of length L equals to 1 meter, in which inlet velocity is 1 meter per second, no viscosity, steady state. So the simplified equation is partial u over partial of x equals to 0, which implies that the velocity constant along the pipe. We will discretize this using the finite volume method on a uniform mesh of let's say 5 cells. So 5 cells centers at x equals to zero point 0.1, 0.3, 0.5, 0.7, 0.9. So here delta x is uniform of zero point 0.2 meter. Step number 2 is that we integrate the PDE over the control volume. Step number 3 is that we approximate the phase values using the linear interpolation between the cell centers. For cell I, the phase values are ui plus 1 divided by 2, and ui minus 1 plus ui divided by 2. And in the fourth step, we assemble the equations as displayed, and in the fifth step, we apply the boundary conditions, and finally we solve them in the step number 6, which actually gives us the exact solution. Our discretization actually reproduced it exactly, because the true solution is linear. For non-linear problems, we get an approximation. We would good get an approximation to it. Now suppose we use the first order operand scheme for the phase values instead of the central differencing. For the flow from left to right, the left phase value of the cell I is just ui minus 1, not the average. Then for the cell 2, u2 minus u1 equals to 0. So this is exactly the same result. So but the equation included the diffusion second derivative. Upwind would introduce numerical diffusion smearing the solution. That is why central differencing, which is of the second order, is preferred for diffusion dominated flows, and upwind first order is used for convection dominated flows to avoid the oscillation. So a trade-off called the Godunov theorem, which is often called as a Godunov theorem. Now we move on to the common pitfalls and how to avoid them. Imagine you have a uniform velocity field, but pressure oscillates high, low, high-low at neighboring cells. A central difference scheme for the pressure gradient might see zero gradient because rho high minus rho low divided by delta of x looks the same um, as p low minus p high divided by delta of x, so they cancel out. The solver thinks the pressure is constant, but it is actually oscillating widely. So this is a checkerboard problem. Solution to it would use a staggered grid, velocity stored at the cell faces, the pressure at the cell centers, or add a range of interpolation to introduce a tiny amount of coupling. All commercial solvers do this invisibly. So if you have a shock wave discontinuous jump in pressure and velocity, a second order central scheme will produce wiggles, overshoots, and undershoots because the Taylor series assumption of smoothness breaks down there. As a solution to this, use the flux limiters or the TVD schemes, total variation diminishing schemes. These automatically switch to first order upwind near the discontinuities and second order elsewhere. In Fluent software and Fluent software, this is the second order upwind scheme option. There is the option, it is not pure central but a limited version. Even with a finite volume method, if your mesh has a non-orthogonal faces, the calculation of the phase flux might not be exact. The solver has to correct iteratively if the non-orthogonality is extreme, which means if it is greater than 70 degree, the mass might not conserve to machine precision. Always check the maximum non-orthogonality in your mesh. Many solvers report it. If it is too high, smooth the mesh and add the polyhedral cells too. So moving on to the summary and the golden rules, let me distill two three rules you can carry with you forever. So the golden rule number one is that smaller is better but slower. uh, Always perform a great independent study. The best mesh is the coarsest mesh uh, that gives you the answer you need. But the golden rule number two is that respect the CFL number two. If your explicit simulation blows up and reduces the delta t, if your implicit simulation has wiggles in it, reduce delta t anyway. And the third and the most important one is that the equation is not the solution. A perfect discretization on a terrible mesh is a beautiful lie. Check the aspect ratio, skewness, orthogonality, and y plus before you believe any result. So, discretization is not just a mathematical technique, it's a mindset. It teaches you that every model is an approximation and every approximation has a cost. Your job as an engineer is to manage that cost, to choose the right slices of bread, the right time steps, the right mesh, so that your simulation is useful, not perfect. As Richard Feynman said, the first principle is that you must not fool yourself, and you are the earliest person to fool. So, do not fool yourself into thinking your discretization is a truth. Understand its limits, and you will be a great CFD engineer. So, I will now answer the questions you might have. So, thank you so much for your attention. We will see you in the next lecture. Thank you.